Dear Bachelor of Science students of Mangalore University, in this video lecture, we are going to discuss triple integrals in rectangular coordinates. A part of Unit 1 of Paper 4 with code MT251 of 4th semester B.Sc credit based semester system revised in the year 2014-15 of Mangalore University. Myself, Dr. Mohandas, Assistant Professor at Department of Mathematics, Srimati Rukmini Shetty Memorial National Government First Grade College and Postgraduate Study Center, Barkuru. Just as double integrals allow us to deal with more general situations than could be handled by single integrals, triple integrals enable us to solve still more general problems. We use triple integrals to calculate the volumes of three-dimensional shapes and the average value of a function over a three-dimensional region. Triple integrals also arise in the study of vector fields and fluid flow in three dimensions. So let us see how to define triple integral of a function. If f of xyz is a function defined on a closed bounded region D in space, such as the region occupied by a solid ball or a lump of clay, then the integral of f over d may be defined in the following way. We partition a rectangular box-like region containing d into rectangular cells by planes parallel to the coordinate axis. So this is the picture we have. We number these cells that lie inside D from 1 to n in some order, the kth cell having dimensions delta xk by delta yk by delta zk and its volume delta vk is equal to the product of these delta xk, delta yk, delta zk as shown in the figure. Now we choose a arbitrary point xk, yk, zk in each of this cell and form the sum Sn equal to the sum k running from 1 to n of the product of delta vk with the function value at xk, yk, zk. We are interested in what happens as D is partitioned by smaller and smaller cells so that delta xk, delta yk, delta zk and the norm of the partition, that is norm P, the largest value among delta xk, delta yk, delta zk all approach 0. When a single limiting value is attained, no matter how the partitions and points xk, yk, zk are chosen, we say that f is integrable over D. As norm P tends to 0 and the number of cells n goes to infinity, the sums Sn approach a limit. We call this limit the triple integral of f over D and write limit n tends to infinity of Sn equal to triple integral of f over D, or limit as norm P tends to 0 of Sn equal to triple integral of D, triple integral over D of the function f. Now how to calculate volume of a region in space using triple integral? If suppose f is the constant function whose constant value is 1, then the sums Sn given by summation of the product of function value with the elementary volume becomes summation delta vk. As delta xk, delta yk and delta zk approach 0, the cells delta vk become smaller and more numerous and fill up more and more of D. We therefore define the volume of D to be the triple integral, that is limit n tending to infinity of the sum of the elementary volumes equal to triple integral of the function 1 over the domain D. So you have the definition. The volume of a closed bounded region D in space is given by V is equal to triple integral of 1 over D. Now how to find the limits of integration in a triple integral? We evaluate a triple integral by applying a three-dimensional version of Puvini's theorem. To evaluate it by 3 repeated single integrations. As with double integrals, there is a geometric procedure for finding the limits of integration for these single integrals. To evaluate the triple integral of f over the domain D, integrate first with respect to z, then with respect to y, finally with respect to x. So there are 4 steps involved here. In the first step, we have to sketch the region D along with its shadow R or the projection, vertical projection of D in the xy plane. Label the upper and lower bounding surfaces of D and the upper and lower bounding curves of R. So you have the figure. Suppose D is of this shape in 3 dimensions. Its projection is in the xy plane is denoted by R. The domain D is bounded above by the surface z equal to f2 of x comma y, and it is bounded below by the surface z equal to f1 of x comma y. The region R, on the left it is bounded by g1 and on the right it is bounded by y equal to g2 of x. So you have this figure now. In the second step, what you have to do is you have to find the limits for z. How do you determine limits of integration for the variable z? Draw a line M passing through a typical point x comma y in R parallel to the z-axis. So fix a point x comma y in the region R with the red dot in the region R. Then take a line passing through this point parallel to the z-axis. As z increases, this line enters D at z equal to f1 of x comma y and leaves at z equal to f2 of x comma y. So these are the lower and upper limits of the variable z. Once you determine the limits of z, you have to determine the limits of y. For that, you have to fix a value of x. Draw a line L through x comma y parallel to the y-axis. As y increases, L enters R at y equal to g1 of x and leaves at y equal to g2 of x. So these are the left and right limits or lower and upper limits of the variable y. Then vary this fixed x to cover the region R and determine the limits of x. So here in this figure, x varies from a to b. Follow similar procedures if you change the order of integration. The projection of region D lies in the plane of the last two variables with respect to which the iterated integration takes place. In the above explanation, the last two variables are y and z, y and x. Z is the innermost variable and x is the outermost variable. So let us take an example. So here you are asked to find the volume of the region D enclosed by the surfaces z equal to x square plus 3y square and z equal to 8 minus x square minus y square. So you know the formula for volume. Volume is triple integral of the function 1 over the domain D. Now you need to find the limits of integration for this variable z, then for the variable y, then for the variable x. So for that you need to sketch the domain D. So let us see these surfaces intersect on the elliptical cylinder. So when you equate z on both the surfaces, you will get the elliptical cylinder x square plus 2y square equal to 4, where z is of course greater than 0. The boundary of the region R, that is the projection of D onto the xy plane, is an ellipse with the same equation x square plus 2y square equal to 4. So when I solve this equation of ellipse for y, I'll get lower and upper limits for y, and that is given by y equal to plus square root of 4 minus x square by 2 and y equal to minus square root of 4 minus x square by 2. So you have the figure here. D looks like this, and the projection is given in the xy plane, that is denoted by R. Now fix a point x comma y in the projection, then the line M parallel to z axis enters the domain at the lower limit and leaves the domain at the upper limit. So you have the lower limit for z and upper limit for z. Similarly, for a fixed x in the domain, in the range of x, y varies from the lower limit to upper limit, or left boundary to right boundary of the projection R. Similarly, this fixed x now can be varied to cover the region R from minus 2 to plus 2. So you have the triple integral with limits z varying from x square plus 3y square to 8 minus x square minus y square, the limits for y, and final limits for x from minus 2 to plus 2. Now when you integrate the innermost integral there with respect to z, that is integration of 1, that is z, when you put the limits, it's upper limit minus lower limit, that simplifies to 8 minus 2x square minus 4y square. Now when you integrate with respect to y, 8 minus 2x square is a constant, so its integral is 8 minus 2x square into y, and integration of minus 4y square, minus 4 is a constant, integration of y square is y cube by 3, and then put the limit for y and simplify, you will get the next step, and on simplification that turns out to be 4 root 2 by 3 integration x varying from minus 2 to plus 2, 4 minus x square power 3 by 2 dx. To evaluate this integral, you need to go for the substitution x equal to 2 sine theta, and on simplification you will get the volume of the region D. Let us take another example. So here is a figure. You are asked to find volume of this domain D. So you can have different ways of finding this volume of this solid. So each of the following integrals gives the volume of the solid shown in the figure. So only the difference in these integrals is the order of integration of the variables. For example, in the first expression for the volume, first we have to integrate with respect to x, then with respect to y, and then with respect to z. So you have to find the projection of this solid on the yz plane, that is the plane formed by the last two variables. So here look into the figure. When you project vertically onto the yz plane, the projection is the triangular region bounded by the coordinate axis, that is y-axis and z-axis, and the line y plus z equal to 1. For a fixed x comma y in this projection, x varies from 0 to the highest value of x, that is 2. So limit for x is 0 to 2, and to cover the projection you fix z. For a fixed z, y varies from left to right. So y varies from 0 to the boundary of this triangle. That is, you have to solve the line y plus z equal to 1 for y. That gives y equal to 1 minus z as upper limit. Similarly, then the limit for z to cover this entire projection, it varies from 0 to 1. So similarly, other order of integration are given. Now we can evaluate one among this. Let us evaluate the integral in part B. So here inner variable is x. When you integrate, it gives x, and put the limit 0 to 2, it gives 2. Then you have to integrate with respect to z. With respect to z, it becomes 2z, and put the limits for z. So it simplifies, and finally integrate with respect to y from 0 to 1. We'll get the value as 1. So volume of this solid given in the figure is 1 cubic units. Now another application of triple integrals. How to find average value of a function in space. The average value of a function f over a region D in space is defined by the formula. Average value of f over D is the ratio of triple integral of f over D to that of volume of D. So let us take an example here. Find the average value of f of x, y, z equal to the product x into y into z over the cube bounded by the coordinate planes and the planes x equal to, y equal to, and z equal to in the first octant. So it's a cube. You know, volume of the cube is 2 into 2 into 2, that is 8 cubic units. And the value of the integral of f over the cubes, you know the limits for the variables. All the three variables varies from 0 to 2, and the function is x into y into z. And when you evaluate, the simple calculation shows that its value is 8. So therefore, average value of this function over the cube is 8 by 8, that is 1. Now let us see some properties of triple integrals. We'll just state these properties. So let us take two functions, capital F and capital G, which are continuous, defined over some domain D. Now triple integral of constant multiple of f is equal to constant multiple of the triple integral of f. This is true for any constant k. K might be 0 also. And the second property says that the triple integral of the sum is sum of the triple integrals, as well as the difference. Triple integral of the difference is difference of the triple integrals. The third property says that if f is a non-negative function, then triple integral of f over the domain D is also non-negative. And if f dominates g over d, then the triple integral of f also dominates triple integral of g over d. The fourth property says the additive property, that if D can be expressed as union of two non-overlapping regions D1 and D2, then triple integral of f over D is triple integral of f over D1 plus triple integral of f over D2. Okay, now let us see some exercise problems based on these concepts which we have discussed, so that the concepts will be clear. Evaluate the following triple integrals by evaluating the iterated integrals. That is, apply Fibonacci theorem to evaluate the following integrals. So I'll take the odd numbered questions from the reference book. So you have the 7th question here, triple integral of x square plus y square plus z square. So the innermost variable is z here. So limit for z is 0 to 1. The next variable is y, and the next and outermost variable is x. When you integrate with respect to z, the innermost integral, x square plus y square is a constant with respect to z. So its integral becomes x square plus y square into z. Put the limit for z, z varies from 0 to 1, plus the integral of z square becomes z cube by 3, then put the limit for z. So on simplification, it becomes x square plus y square plus 1 by 3. This has to be integrated with respect to y. Again, x square plus 1 by 3 is a constant with respect to y. So integration gives x square plus 1 by 3 into y, and integration of y square is y cube by 3. Now put the limits for y, that is from 0 to 1, and simplify, and finally integrate with respect to x. So that gives again 1 by 3 plus 1 by 3, that is 2 by 3 is a constant, so 2 by 3 into x plus integration of x square is x cube by 3, and when you put the limits you'll get the value as 1. Next question is triple integral limits for x, y, z all varies from 1 to e of 1 by x, y, z with respect to x, y, z. So in our first variable is x, then y, then the outermost variable is z. So when you integrate with respect to x, 1 over yz is a constant, and integration of 1 by x is log x, natural log. Put the limit 1 to e, so log e is 1 minus log 1 is 0. So then integrate with respect to y, 1 by z is a constant, integration of 1 over y is log y, put the limits 1 to e, log is 1 minus log 1 is 0 again, so it gives 1 by z, and finally when you integrate with respect to z, it gives log z, and between the limits 1 to e, it turns out to be 1. Question number 11 you have limit for z, outermost limit for z 0 to 1, then y 0 to pi, x the inner variable from 0 to pi. So when you integrate with respect to x, y and z are constants, so sin z is also constant, so integration becomes y sin z into x, put the limits 0 to pi, so it becomes y sin z into pi. When you integrate with respect to y, sin z and pi are constants, integration of y is y square by 2, put the limit 0 to pi, and finally integrate with respect to z, integration of sin z is minus cos z, and when you put the limit 0 to 1, it becomes 1 minus cosine 1 into pi cube by 2. Question number 13. Innermost variable is z. Limit for z is given as 0 to square root of 9 minus x square. Next variable is y, and outermost variable is x. So when you integrate with respect to z, it is integration of 1, that is z, put the limits, then integrate with respect to y, square root of 9 minus x square is a constant, so its integral is constant times y, and then put the limits, becomes 9 minus x square, and when you finally integrate with respect to x, 9x between 0 to 3 minus x cube by 3 between 0 to 3, that is 18. Question number 15. Okay, now most variable is z, so integrate, put the limits, it turns out to be 2 minus x minus y, then integrate with respect to y, 2 minus x is constant, integral of y is y square by 2, evaluate by putting the limits, and then finally integrate with respect to x, so that turns out to be 7 by 6. Question number 17. Okay, now here a small change, instead of the variables x, y, z, we have the variables u, v, w. So in the u, v, w space you have a domain and a continuous function, cosine function is given, you have to integrate. So innermost variable is u. When you integrate cosine function, integral of cosine is sine, and then put the limit for u 0 to pi, and evaluate the upper limit and lower limit. So then you have to integrate with respect to v. Again, integral of sine is minus cosine, and minus sign becomes plus cosine, put the limits, then you will get integration in terms of w. Again integrate and put the limits, and observe that sine 3 pi, sine 2 pi, sine pi, all these are zeros, so value of the integral is 0. Question number 19. Here again the variables are in the t, v, x space. So innermost variable is x. When you integrate with respect to x, e power x remains as e power x. So put the limits minus infinity to 2t. I mean lower limit. Actually you have to take the limiting case as b tending to minus infinity, but we can write in this form. So upper limit is 2t, e to the power 2t, lower limit e to the power minus infinity. So it's actually becoming smaller and small as power becomes larger and large because of the presence of minus sign there. So it finally tends to 0. So when you evaluate the integral of e power 2t, it is e power 2t by 2 between the limit 0 to log secant v, and you can simplify this, and it turns out to be half minus pi by 8. Go through the steps. Okay, now in the next following questions we have to find volumes using triple integrals. So here is the region of integration of the integral. So limits are given. Innermost variable is z, next is y, and outermost variable is x. So rewrite the integral as an equivalent iterated integral in different orders. So in question number A, you have to write in the order dy, dz, dx. So to do that, y is the innermost variable. So you have to project the solid to the xz plane. Now when you project this particular solid into the xz plane, what happens? That you have to determine. Now if you see the intersection of the surfaces here, one is the surface y equal x square, that's surface of the cylinder, and the top surface is y plus z equal to 1. The intersection y equal x square you have to substitute there, so it is z plus x square equal to 1. So this is the intersection. This you have to project into the xz plane. So equation remains the same. So that is z plus x square equal to 1. And when you put the limit for y, so fix a point on the projection. Projection is in the xz plane. Y varies from left to right from 0. Y varies from the lowermost surface, that is leftmost surface here, that is the surface of the cylinder, y equal x square, parabolic cylinder, and the upper limit is you have to solve the equation y plus z equal to 1 for y, that is 1 minus z. Now in the projection, as I told, projection is x square plus z equal to 1. When you solve for z, because the next variable is z, z varies from 0 to z is equal to 1 minus x square. Then finally, to cover the projection by varying x varies from minus 1 to plus 1. Similarly, the other expressions are given. And the next question, the region between the cylinder z equal to y square and the xy plane, that is bounded by the planes x equal to 0, x equal to 1, y equal to minus 1, y equal to plus 1. So this is the solid. What you have, you are required to find volume of this solid. So you can project this into the xy plane. When you project this solid into the xy plane, it becomes a rectangle there. It becomes a rectangle. So fix a point on the rectangle x comma y and see what is the variation for the variable z. So for any fixed x comma y in the projection R, z varies from 0, that is the lower value of z, and the upper value is the curved surface of the cylinder z equal to y square. So upper limit is y square. Then you have to integrate over the projection. So to cover the projection, fix x, y varies from minus 1 to plus 1, and this fixed x varies from 0 to 1. Integrating with respect to z, it gives integration of 1, that is y square itself. Then integrate with respect to y, it becomes y cube by 3, put the limit, and then integrate with respect to x, it gives 2 by 3 cubic units as the volume of this solid. Find the volume of the region in the first octant bounded by the coordinate planes and the plane y plus z equal to 2 and the cylinder x equal to 4 minus y square. So sketch these surfaces in the three-dimensional space. You always go for a right-handed system. When you rotate from x to y through 90 degrees, z, the direction in which the right-handed screw moves gives the direction of z. It's the right-handed system. So this is a figure you have. Again, you can project it on the xy plane and fixing a point x comma y in the xy plane. Z varies from 0 to, as lower limit, to upper limit, that is surface to the surface y plus z equal to. When you solve for z, it becomes 2 minus y. Then cover the projection. In the projection, I'll fix y first. When you fix y, x varies from 0 to the right, to the rightmost boundary as 4 minus y square, that is surface of the cylinder. The limit for y varies from left to right, that is 0 to 2, to cover the entire region R. So integration is simple here. Integration with respect to x, 2 minus y is a constant. So upper limit minus lower limit. On simplification, you will get this cubic expression. And then finally integrate with respect to y. And put the limits, you will get it as 20 by 3 cubic units. Next question. The tetrahedron in the first octant bounded by the coordinate planes and the plane passing through these 3 points 1, 0, 0, 0, 2, 0 and 0, 0, 3. Again, you can project this in the xy plane. It becomes the triangular region. For any fixed point in the projection, z varies vertically up from lower limit 0 to the slant surface here. So what is the equation of the slant surface? That you need to determine. So equation of that plane passing through these 3 points with coordinate intercepts, equation becomes x by 1 plus y by 3 plus z by 2 equal to 1, or 6x plus 3y plus 2z equal to 6. This is the surface, upper surface. So limit for z varies from 0 to, solve for z in terms of x and y. So it becomes 1 over 2 of 6 minus 3y minus 6x. Then integrate this over the projection R. So to cover the projection R, which is a triangular region, and you know how to cover it, y varies from 0 to 1 by 3 times 6 minus 6x. Okay, this upper limit is evaluated by putting z equal to 0 in this plane. Thus you will get a boundary here in the projection. Now integrate with respect to y. It is a simple task, algebraic expression you have. Then substitute the limit for y. You simplify this and integrate with respect to x from 0 to 1. It becomes 1. So 1 unit cube is the volume of this tetrahedron. Find the volume of the region common to the interiors of the cylinders. One is the horizontal cylinder, x square plus y square equal to 1. This is the vertical cylinder, of course. The other one, x square plus z square equal to 1, is the horizontal cylinder. Okay, 1/8 of which is shown in the accompanying figure. In the figure you can see the darker part there. There's a mixture of pink and blue color. Somewhat it looks violet color. That part is given. So you have to find entire volume. So volume becomes 8 times the volume bounded here. So again you project it on the xy plane and fix a point on the projection. See the variation in z. Z varies from lower limit, that is 0, to the upper limit. Upper limit is the surface of the horizontal cylinder. So solve for z. Z gives plus square root of 1 minus x square, because z is positive here. Then integrate with respect to z. Integration of 1 is z. So put the limit. It is upper limit minus lower limit. Lower limit is 0. So it is just the upper limit. Then cover the projection in terms of y and x. So fix x and see what is the variation in y in the projection. So it is a boundary of that cylinder in the xy plane, the vertical cylinder. So solving for y, it is again positive there y. So plus square root of 1 minus x square. And x varies of course from 0 to 1, the radius of that circular part. So when you integrate with respect to y, square root of 1 minus x square is a constant. So that into upper limit minus lower limit. So that becomes 1 minus x square. When you integrate with respect to x, it is 16 by 3 cubic units. Here you are required to find the volume of the region in the first octant bounded by the coordinate planes. The plane x plus y equal to 4 and the cylinder y square plus 4z square equal to 16. So this is the region you have. Again you can project it on the xy plane. Call it as the R as the projection. For a fixed point in the projection, z varies from lower limit 0 to the upper limit. Upper limit is from this cylinder. So solving for z, which is 1 by 2 times square root of 16 minus y square. Then cover the region R in terms of the variables y and x, or x and y in any order. Okay, here we have covered in terms of x first and then with respect to y. So when you integrate, of course, with respect to z, it is half in square root of 16 minus y square. Then with respect to x, when you integrate, this is a constant, so upper limit is 4 minus y. Now put y equal to 4 sin theta, so that this could be simplified. Limits become 0 to pi by 2, and on simplification using trigonometric relation, cos square theta, I will put it as cos 2 theta plus 1 by 2, and on integration you go through the steps given here one by one. Then you will find out the answer as 8 by 3 pi minus 4 cubic units. Yeah, this is the reference book, Thomas Calculus, 3 author book, 11th edition, Pearson Publications, published in the year 2008. We covered chapter 15, sections 15.1, 15.2, 15.3 and 15.4. All the best for your final examination. Thank you.